Hello, my name is Brian Doe, and I'll be presenting our work on a lightweight, high-extension 3-degree of freedom manipulator using pinched bistable tapes. High-extension, lightweight robot manipulators have the potential to enable physical interaction in difficult-to-reach environments. One emerging scenario for such manipulators is aerial manipulation, in which aerial robots physically interact with their environment. However, this currently poses many research challenges. For example, robot arms with revolute joints used on drones must undergo complex self-folding for stowage during landing. Retractable arms could address this issue, but prior work has focused on retractable arms with just a single degree of freedom, limiting their reach. In this work, we demonstrate a low-cost, high-extension, planar, 3-DOF cable-driven manipulator shown here. The manipulator consists of 3 main parts. First, 2 bistable tapes are arranged back to back. Second, a revolute joint is formed by pinching the tapes together using a pinching node. And third, the tapes and cables are stored in motorized cable and tape spools. Back-to-back bistable tapes form the backbone of the manipulator. Bistable tapes, also referred to as tape springs, are fabricated with a transverse curvature, which greatly increases their longitudinal bending stiffness. They can be stored around spools, enabling deployable structures with high extension ratios, such as antenna booms. We use tape springs from off-the-shelf tape measures in our work. Prior work has used bent tape springs to form hinges, but this bending process has been subject to a snap-through instability. This makes it infeasible to control small bend angles with such hinges. To increase the overall arm stiffness and enable more precise control of small angles in our design, we place bistable tapes back to back and form a hinge through changing the transverse curvature to locally flatten the tape. Through pinching the tapes, we locally set the transverse curvature to 0, which greatly reduces the energy required to locally bend. We conducted an experiment with back-to-back tapes and demonstrated how pinching can eliminate the snap-through instability. This pinching is accomplished through a pinching node, which consists of 2 motorized rollers. The spacing between the 2 rollers is preset such that the tape must flatten when passing through. We can observe this behavior in the video to the right. The node uses the tapes as a linear track, and by moving up or down the tape, it can alter the location of the pinch, creating a movable revolute joint. Finally, there are 2 additional sets of motorized spools, one set which controls the extension and retraction of the tapes, and the other which controls the lengths of the 2 cables which run along the side of the arm. By changing the cable lengths, we can bend the arm. Now, I will briefly highlight a few of the demonstrations which we conducted. This video illustrates the 3 control inputs of the bistable tape manipulator performed sequentially. First, we have length change of the tape. This can be either extension or retraction. Second, we have movement of the pinching node along the tape. And finally, we have tensioning of the individual cables, which produces bending of the overall manipulator. In this paper, we derived a kinematic model which relates the position and orientation of the end effector as a function of the control inputs of the tape and the position of the pinching node. The position of the pinching node is independent of the arm length. By controlling both, we can maintain a constant node position. We show examples of achieving various end effector positions and our ability to achieve different orientations for a single position. We also show how we can maintain a given end effector angle independent of the length of the manipulator and the ability of the manipulator to lift weights, such as the 200-gram weight shown on the right, to specified angles. In the future, we plan on refining this proof of concept design, further characterizing and investigating failure modes and dynamic control, and ultimately incorporating this manipulator with an aerial robot. Thank you all for listening.